In the golden light of dawn, as the sun rises over the endless desert sands of Egypt, three magnificent monuments pierce the horizon like ancient sentinels guarding secrets from the dawn of civilization. The pyramids of Giza stand as they have for over 4,000 years, their massive stone blocks weathered by countless seasons, yet still defying time itself. These are not merely tombs or monuments, but puzzles carved in limestone and granite, riddles that have captivated human imagination for millennia. The Great Pyramid, the largest of these mysterious structures, contains over 2,300,000 individual stone blocks. Each block weighs between 2 and 80 tons, yet they fit together with a precision that would challenge even our modern construction methods. The original height reached 146.6 meters into the sky, making it the tallest human-made structure on Earth for nearly 4,000 years. When we consider that the ancient Egyptians built this marvel without steel tools, without wheels, and without cranes, the achievement becomes almost incomprehensible. What makes these monuments even more mysterious is their perfect alignment with the cardinal directions. The Great Pyramid faces true north with an error margin of less than 0.05 degrees. This level of precision suggests knowledge and planning that seems almost impossible for a civilization we often think of as primitive. The pyramid's base, covering 13 acres, varies in height by less than 1 inch across its entire foundation. Such accuracy would be impressive even by today's engineering standards. For thousands of years, travelers, scholars, and dreamers have stood in the shadow of these stone giants, wondering how they came to be. Ancient Greek historians marveled at them. Medieval Arab scholars tried to unlock their secrets. Modern archaeologists and engineers continue to debate their construction methods. Each generation brings new theories, new discoveries, and new questions. Tonight we embark on a gentle journey into one of humanity's greatest mysteries. We will explore not just how these monuments were built, but why they continue to capture our imagination. In the soft darkness of evening, let us travel back in time to an era when pharaohs commanded the loyalty of thousands, when the Nile River was the highway of an empire, and when human ambition was measured not in years, but in millennia. The pyramids represent something profound about human nature, our desire to create something lasting, something that speaks to the stars themselves. They are monuments to the power of human cooperation, the triumph of vision over limitation, and the eternal human quest to leave something beautiful behind. As we begin this exploration, we invite you to imagine the sounds of ancient construction sites, the voices of workers singing as they hauled massive stones, and the quiet satisfaction of builders who knew they were creating something for eternity. These stone giants hold their secrets close, but they also offer us glimpses into a world where the impossible became possible, where dreams took shape in stone, and where the boundary between earth and sky was bridged by human determination and ingenuity. To truly understand the mystery of the pyramids, we must first appreciate the sheer magnitude of what the ancient Egyptians accomplished. Imagine standing at the base of the Great Pyramid today, craning your neck to see its apex disappearing into the desert sky. The structure before you represents one of the most ambitious construction projects ever undertaken by human hands, a monument that required the coordination of thousands of workers, the transportation of millions of tons of stone, and the precise execution of plans that would challenge even our modern engineering capabilities. The Great Pyramid of Khufu, built around 2500 BC, originally stood at a height of 146.6 meters, equivalent to a modern 47-story building. Its base covers an area of 13 acres, and if you were to walk around its perimeter, you would travel nearly 1 kilometer. The entire structure contains approximately 2,300,000 individual stone blocks, with an estimated total weight of over 6 million tons. To put this in perspective, the pyramid weighs more than 16 Empire State Buildings combined. Each stone block in the pyramid tells its own story of human ingenuity and determination. The average block weighs about 2.5 tons, roughly the weight of a large automobile. But some blocks, particularly those used in the internal chambers, weigh as much as 80 tons. These massive granite blocks, some of which form the ceiling of the king's chamber, were transported from quarries in Aswan, over 800 kilometers away. The precision with which these blocks were cut and fitted is remarkable. The joints between stones are so tight that you cannot slide a knife blade between them, and many blocks were fitted without any mortar at all. The pyramid's orientation reveals another layer of the mystery. The structure is aligned to the cardinal directions with an accuracy that astounds modern surveyors. The eastern side deviates from true east by only 5.5 arc minutes, while the western side deviates by only 2.5 arc minutes. This level of precision suggests that the ancient builders had sophisticated methods for determining true north, possibly using star observations or solar measurements that we are only beginning to understand. The internal structure of the pyramid is as impressive as its external dimensions. The monument contains a complex network of passages, chambers, and shafts that demonstrate advanced understanding of engineering principles. The Grand Gallery, a corbelled passage that rises at a 26-degree angle, showcases sophisticated architectural techniques. The King's Chamber, constructed entirely of granite, features a roof composed of 9 massive blocks arranged in a way that distributes the enormous weight of the stones above. Perhaps most remarkable is the speed at which this monument was constructed. Archaeological evidence suggests that the Great Pyramid was built over a period of approximately 20 years during the reign of Pharaoh Khufu. This means that the builders had to quarry, transport, and precisely place an average of 300 blocks per day, every day for 2 decades. During peak construction periods, this number would have been even higher, possibly reaching 800 blocks per day. The mathematical precision embedded in the pyramid's design continues to fascinate researchers. The ratio between the pyramid's height and the perimeter of its base approximates the mathematical constant pi, though whether this was intentional or coincidental remains a subject of debate. The angle of the pyramid's slopes, approximately 51 degrees and 52 minutes, creates a structure that appears to maintain perfect proportions from any viewing angle. When we consider the tools and technology available to the ancient Egyptians, the achievement becomes even more extraordinary. They had no iron tools, relying instead on copper chisels and dolerite hammers. They had no wheels, no pulleys, and no cranes. Their most sophisticated lifting device was likely the lever, and their primary means of transportation was the wooden sledge. Yet with these simple tools, they created a monument that has stood for over 4.5 millennia. The precision of the pyramid's construction extends beyond its external appearance to its internal chambers and passages. The floors are level, the walls are plumb, and the corners are square to a degree that would be considered excellent workmanship even today. The passages that lead to the burial chambers maintain consistent dimensions throughout their length, and the chambers themselves are constructed with joints so precise that modern restoration work is barely noticeable. The Great Pyramid was not built in isolation but as part of a complex that included smaller pyramids, temples, and causeways. The entire Giza complex represents a unified architectural vision that required decades of planning and construction. The relationship between the 3 main pyramids, their alignment with specific stars, and their connection to the surrounding landscape reveals a sophisticated understanding of both engineering and astronomy. The psychological impact of the pyramid's scale cannot be understated. Standing before this monument, ancient visitors would have been overwhelmed by its size and perfection, just as modern tourists are today. The pyramid was designed to inspire awe, to demonstrate the power of the pharaoh, and to serve as a bridge between the earthly and divine realms. Its scale was not merely functional but symbolic, representing the pharaoh's ability to mobilize the resources of an entire kingdom in service of eternal life. The construction of the Great Pyramid required not just skilled labor, but also sophisticated logistics. The builders needed to coordinate the work of quarrymen, transporters, stonemasons, and architects. They needed to ensure a steady supply of food, water, and tools for thousands of workers. They needed to maintain quality control across decades of construction. The organizational skills required for such a project rival those of any modern construction undertaking. Modern attempts to understand the pyramid's construction have involved computer modeling, experimental archaeology, and detailed analysis of the structure itself. These studies have revealed the incredible precision of the ancient builders and the sophistication of their techniques. Yet many questions remain unanswered. How did they achieve such accuracy without modern surveying equipment? How did they lift the heaviest stones to the upper levels? How did they maintain such consistent quality across such a long construction period? The Great Pyramid continues to challenge our understanding of ancient capabilities. It stands as a testament to human ambition, ingenuity, and the power of organized effort. As we contemplate its massive stones and perfect proportions, we are reminded that the ancient world was not primitive but sophisticated in ways we are only beginning to appreciate. The pyramid is not just a tomb or a monument, but a masterpiece of engineering that continues to inspire wonder and respect nearly 5,000 years after its completion. To answer how it was built, we must first understand what we are truly dealing with. The Great Pyramid is not merely a large pile of stones, but a precisely engineered structure that represents the pinnacle of ancient architectural achievement. Its construction required knowledge, skill, and resources that challenged the limits of what was possible in the ancient world. Understanding this scale and complexity is the first step in unraveling the mystery of how these stone giants came to be. The magnitude of the challenge becomes even more apparent when we consider the environmental conditions under which the pyramid was built. The desert climate of Egypt, with its scorching days and cold nights, would have made construction work extremely difficult. Workers would have labored under the blazing sun, their copper tools becoming too hot to handle without protection. The sand would have been a constant adversary, filling in excavations and making precise measurements challenging. Yet somehow, the ancient builders overcame these obstacles to create a monument of extraordinary precision. The logistics of feeding and housing the workforce presents another dimension of the challenge. Archaeologists estimate that during peak construction periods, the pyramid site would have been home to between 20,000 and 30,000 workers. These people needed food, water, shelter, and medical care. The surrounding desert offered none of these necessities naturally. Everything had to be transported from the fertile Nile Valley, creating a supply chain that stretched across the Egyptian kingdom. The organizational skills required to maintain such a large workforce in the desert for decades represents an achievement in itself. The quarrying process alone represents a monumental undertaking. The limestone blocks that form the pyramid's core were quarried from the Giza plateau itself, creating vast excavations that can still be seen today. The precision cutting of these blocks, each weighing several tons, required skilled craftsmen who could work with copper tools and stone hammers. The granite blocks used in the internal chambers came from quarries in Aswan, hundreds of kilometers to the south. These blocks, some weighing as much as 80 tons, had to be cut from the living rock using techniques that archaeologists are still trying to understand. The transportation of materials to the construction site created challenges that would test any ancient civilization. The limestone blocks from local quarries had to be moved across the uneven desert terrain. The granite blocks from Aswan had to be transported by river barge during the annual flood season, then somehow moved from the Nile to the construction site. The precision required to move these massive stones without damaging them or the existing structure demonstrates a level of engineering sophistication that challenges our assumptions about ancient capabilities. The construction site itself would have been a marvel of organization and planning. Multiple crews would have worked simultaneously on different aspects of the project. Some would be preparing the foundation, others would be cutting and fitting stones, while still others would be working on the internal chambers and passages. The coordination required to ensure that all these activities proceeded smoothly and that the finished structure would meet the exacting standards evident in the completed pyramid represents the achievement in project management that rivals any modern construction undertaking. The precision of the pyramid's construction becomes even more remarkable when we consider the cumulative effect of small errors. In a structure containing over 2 million stone blocks, even tiny inaccuracies in cutting or placement would compound over time, eventually making it impossible to maintain the pyramid's geometric perfection. Yet the ancient builders achieved a level of accuracy that suggests they had methods for detecting and correcting errors throughout the construction process. The mystery deepens when we consider the internal structure of the pyramid. The passages and chambers were not added after the pyramid was completed, but were built as the structure rose. This required the builders to maintain precise alignment and dimensions for passages that extended hundreds of meters through the interior of the pyramid. The Grand Gallery, with its corbelled ceiling and precise dimensions, had to be built while the pyramid was under construction. requiring the builders to work in confined spaces with limited light. The acoustic properties of the pyramid's internal chambers add another layer to the mystery. The king's chamber, when empty, produces a resonant frequency that some researchers believe was intentional. The design of the passages creates unique acoustic effects that may have had religious or ceremonial significance. Whether these properties were planned or accidental remains unknown, but they demonstrate the sophisticated understanding of architectural principles that the pyramid's builders possessed. The pyramid's relationship to the surrounding landscape reveals another aspect of the challenge faced by its builders. The structure is positioned to take advantage of the natural contours of the Giza plateau, but it also required extensive modification of the terrain. The builders had to level the building site, create drainage systems, and construct approaches for transporting materials. The careful integration of the pyramid with its environment suggests a comprehensive understanding of both engineering and landscape architecture. The preservation of the pyramid over nearly 5 millennia presents its own mystery. The structure has survived earthquakes, sandstorms, and human interference while maintaining its essential form. The techniques used to join the stones, the selection of materials, and the overall design all contributed to the pyramid's longevity. Understanding how the ancient builders created a structure capable of surviving for thousands of years provides insights into their sophisticated understanding of materials science and structural engineering. The challenge of building the Great Pyramid extended beyond the physical and technical aspects to encompass social and political dimensions. The project required the mobilization of resources from across the Egyptian kingdom, the coordination of different skilled crafts, and the maintenance of worker morale over decades. The successful completion of the pyramid demonstrates not just technical skill, but also the effectiveness of ancient Egyptian administrative and organizational systems. As we contemplate the full scope of the challenge faced by the pyramid builders, we begin to appreciate the magnitude of their achievement. They overcame obstacles that would daunt modern engineers, using tools and techniques that seem inadequate for the task. Yet they succeeded in creating a monument that continues to inspire awe and wonder nearly 5,000 years after its completion. The scale of their achievement serves as a reminder that human ingenuity and determination can overcome seemingly impossible challenges, creating works of lasting beauty and significance. For generations, popular imagination has painted a picture of the pyramid builders as masses of enslaved people, whipped and driven by cruel overseers to construct monuments to pharaonic vanity. This dramatic vision, reinforced by Hollywood movies and sensational books, has captured the public consciousness for decades. Yet archaeological evidence tells a very different story, one of skilled craftsmen, organized work crews, and a society that took immense pride in creating something eternal. The truth about who built the pyramids is far more fascinating than the fiction. The myth of slave labor began with ancient historians like Herodotus, who visited Egypt centuries after the pyramids were built and recorded the stories told to him by local guides. These tales, already distorted by time and retelling, described vast armies of oppressed workers laboring under harsh conditions. The image was further reinforced by biblical accounts of Hebrew slavery in Egypt, though these stories likely refer to different periods and different construction projects. Modern archaeology has systematically dismantled these misconceptions, revealing instead a complex society of skilled professionals working together on a project of national importance. The first clues about the true nature of the pyramid builders came from discoveries made in the 1990s near the Giza plateau. Archaeologists uncovered extensive workers' villages, complete with dormitories, bakeries, breweries, and what appear to be medical facilities. These were not the crude barracks one might expect for enslaved laborers, but well-organized communities designed to house and care for a large workforce. The remains of these settlements paint a picture of a society that valued the health and welfare of its workers, understanding that the success of the massive construction project depended on maintaining a healthy, motivated workforce. The workers' cemetery, discovered adjacent to these villages, provides even more compelling evidence about the pyramid builders. The graves contain the remains of men and women who clearly engaged in heavy physical labor, as evidenced by the wear patterns on their bones and the evidence of healed fractures. Yet these same graves also show signs of medical care. Broken bones had been set and allowed to heal properly. Some individuals show evidence of surviving serious injuries that would have been fatal without skilled medical attention. This suggests that the pyramid builders had access to medical care that was quite advanced for its time. The diet of the pyramid builders reveals another aspect of their status in Egyptian society. Analysis of food remains from the workers' villages shows that these people ate well by ancient standards. Their diet included bread, beer, onions, garlic, and generous portions of meat, particularly beef and fish. The quantity of cattle bones found at the site suggests that the workers consumed meat regularly, a luxury that would have been available only to people of relatively high status in ancient Egypt. This nutritious diet would have been essential for maintaining the strength and health needed for the demanding physical work of pyramid construction. The organization of the workforce reveals a sophisticated understanding of human resources and project management. Rather than employing a single massive workforce continuously, the Egyptians appear to have used a system of rotating crews. During the agricultural off-season, when the Nile flood made farming impossible, workers from across Egypt would come to Giza to participate in the construction project. This system allowed farmers to contribute to the national project while maintaining their agricultural activities during the growing season. It also provided a steady supply of fresh workers, preventing the exhaustion and demoralization that might have affected a permanent workforce. The workforce was organized into crews with distinctive identities and friendly rivalries. Inscriptions found in the pyramid and on blocks used in construction reveal crew names like Friends of Khufu and Drunkards of Menkaura. These names suggest a sense of camaraderie and competition among the different work groups. The crews appear to have taken pride in their work and their association with the pharaoh, viewing pyramid construction not as punishment, but as an honor and a sacred duty. The skilled craftsmen who worked on the pyramids represented the elite of Egyptian society. Stonemasons, carpenters, metalworkers, and architects would have been highly valued professionals whose skills were essential to the project's success. These craftsmen likely trained for years to master their trades, and their expertise would have been passed down through generations. The precision evident in pyramid construction suggests that these skilled workers took great pride in their craftsmanship and were given the time and resources necessary to do their work properly. The administrative structure required to coordinate the pyramid workforce was itself a remarkable achievement. Scribes kept detailed records of work assignments, material deliveries, and worker attendance. Supervisors coordinated the activities of different crews and ensured that work proceeded according to plan. Engineers and architects provided technical guidance and quality control. This bureaucratic structure required literacy, numeracy, and organizational skills that demonstrate the sophistication of Egyptian administration during the Pyramid Age. The seasonal nature of pyramid construction work created a unique social dynamic. During the flood season, the Giza Plateau would have been transformed into a bustling city, with workers arriving from throughout Egypt to participate in the great project. These workers would have brought with them the customs, dialects, and traditions of their home regions, creating a cosmopolitan atmosphere that was unusual for the ancient world. The interaction between workers from different parts of Egypt may have helped strengthen national identity and unity. The role of women in pyramid construction is less well documented, but evidence suggests that they played important supporting roles. Women are buried in the workers' cemetery, indicating that they were part of the construction community. They likely worked in food preparation, textile production, and other essential services that supported the workforce. Some may have been skilled craftswomen in their own right, contributing specialized knowledge to the construction project. The religious aspect of pyramid construction cannot be overlooked when considering who the builders were. For the ancient Egyptians, participating in the construction of the pharaoh's eternal resting place was a religious act that would bring spiritual benefits to the workers themselves. The pyramid was not just a tomb but a machine for ensuring the pharaoh's successful transition to the afterlife, which was believed to benefit all of Egypt. This religious motivation would have provided powerful incentive for workers to contribute their best efforts to the project. The training and skill development required for pyramid construction created a legacy that extended far beyond the monuments themselves. The techniques and knowledge developed during pyramid construction were passed down through generations of Egyptian craftsmen, influencing architecture and engineering throughout Egyptian history. The pyramid builders were not just construction workers, but the founders of a tradition of excellence that would characterize Egyptian monumental architecture for centuries. The international character of the pyramid workforce adds another dimension to our understanding of who built these monuments. While the majority of workers were certainly Egyptian, evidence suggests that skilled craftsmen from other regions may have contributed their expertise to the project. This international cooperation demonstrates the reputation and prestige of the Egyptian kingdom during the Pyramid Age, attracting talented individuals from across the ancient world. The pyramid builders were not anonymous masses, but individuals with names, families, and personal stories. Some of their names have been preserved in inscriptions, allowing us to glimpse the human faces behind the monumental achievement. These inscriptions reveal men and women who took pride in their work and their contribution to something greater than themselves. They saw themselves not as oppressed laborers, but as participants in a great national enterprise. The social mobility available to pyramid builders represents another aspect of their identity. Skilled workers could advance within the construction hierarchy, eventually becoming supervisors or specialists in particular crafts. This opportunity for advancement would have provided additional motivation for workers to excel in their duties. The pyramid construction project offered a path to social and economic improvement that was rare in the ancient world. The legacy of the pyramid builders extends beyond their immediate achievement to influence our understanding of ancient societies and human capabilities. These were not primitive people driven by fear and oppression, but skilled professionals working together to achieve something unprecedented. Their story reminds us that great achievements throughout history have been accomplished by ordinary people working together with extraordinary dedication and skill. As we contemplate the true identity of the pyramid builders, we see reflected in their story timeless human qualities: pride in craftsmanship, dedication to a common purpose, and the desire to create something lasting and beautiful. They were farmers and craftsmen, engineers and laborers, men and women who came together to build monuments that would outlast their civilization. Their achievement stands as a testament to the power of human cooperation and the heights that can be reached when people work together toward a common goal. In our modern world of steel and machinery, it seems almost impossible to imagine constructing something as massive and precise as the Great Pyramid using only the simplest of tools. Yet, this is exactly what the ancient Egyptian builders accomplished, relying on copper, stone, wood, and rope to create monuments that have endured for millennia. The story of these humble tools and the ingenious ways they were employed reveals as much about human creativity and determination as it does about ancient technology. Each tool tells a tale of innovation born from necessity, of craftsmen who pushed the boundaries of what was possible with the materials at their disposal. The most fundamental tool in the pyramid builder's arsenal was the copper chisel. In an age before ironworking had been mastered, copper represented the hardest metal available to Egyptian craftsmen. These chisels, carefully forged and shaped by skilled metalworkers, were the primary instruments for cutting and shaping the limestone blocks that formed the pyramid's core. The copper used in these tools was often alloyed with small amounts of arsenic or tin, creating a harder edge that could withstand the rigors of stone cutting. Yet even these improved copper tools were far softer than the iron and steel implements we use today. The limitations of copper tools created unique challenges for the pyramid builders. Copper chisels would dull quickly when used against hard stone, requiring frequent resharpening. A single chisel might need to be resharpened several times during a day's work, and the constant resharpening would gradually reduce the size of the tool until it became unusable. Archaeological evidence from pyramid construction sites reveals vast quantities of worn copper tools, testament to the enormous amount of metalwork required to keep the construction crews supplied with sharp implements. The process of resharpening copper tools was itself a skilled craft. Metalworkers would heat the dulled chisels in charcoal fires, hammer them back into shape, and carefully work the cutting edge to restore its sharpness. This constant cycle of use, resharpening, and reuse meant that the pyramid construction sites required not just stoneworkers but also a substantial population of metalworkers dedicated solely to tool maintenance. The logistics of keeping thousands of workers supplied with sharp tools represents a significant organizational challenge that the ancient Egyptians managed with remarkable efficiency. Beyond copper chisels, the pyramid builders relied heavily on stone tools, particularly hammers made from dolerite, a hard volcanic rock. These dolerite pounders, as archaeologists call them, were used for the initial rough shaping of limestone blocks and for breaking larger stones into manageable pieces. The hardness of dolerite made it ideal for this purpose, and the stones could be shaped into effective hammers by skilled craftsmen. Unlike copper tools, dolerite hammers would not dull in the same way, though they would eventually crack and break from repeated use. The technique of using dolerite hammers required considerable skill and experience. Workers would strike the limestone in specific patterns, following natural fault lines in the stone to achieve clean breaks. The rhythm and force of the hammer blows had to be carefully controlled to avoid shattering the stone or creating irregular surfaces. Master stoneworkers would train apprentices in these techniques, passing down knowledge that had been refined over generations of pyramid construction. Wooden tools played a crucial role in pyramid construction, though their organic nature means that fewer examples have survived for archaeological study. Wooden levers were essential for moving and positioning heavy stone blocks. These levers, made from strong hardwoods, could amplify human strength dramatically, allowing small teams of workers to move stones weighing several tons. The principle of leverage was well understood by Egyptian engineers, who designed wooden beams specifically for stone-moving operations. The wooden sledges used to transport stone blocks represent another triumph of simple but effective engineering. These sledges, constructed from strong wooden planks and beams, could carry enormous loads across the desert sand. The runners of the sledges were often reinforced with copper or bronze strips to reduce wear, and the entire structure was designed to distribute weight evenly to prevent the sledge from breaking under its load. Teams of workers would pull these sledges using ropes, sometimes with the assistance of oxen or other draft animals. Rope was perhaps the most versatile tool available to pyramid builders. Egyptian rope makers created strong, durable ropes from papyrus fibers, flax, and other plant materials. These ropes were used for hauling stone blocks, operating simple pulleys, and securing loads during transport. The strength and flexibility of Egyptian rope was crucial to many construction operations, and the rope makers were skilled craftsmen whose products had to meet exacting standards for strength and durability. The technique of rope making itself was a complex craft requiring specialized knowledge. Fibers had to be properly prepared, twisted into strands, and then woven together to create ropes of various thicknesses and strengths. Different types of rope were needed for different purposes, from thin cords used for measuring and marking to thick hawsers capable of bearing enormous loads. The quality of rope could mean the difference between success and disaster in critical lifting operations. Egyptian builders also made extensive use of measuring and marking tools that, while simple in design, were remarkably accurate in practice. The cubit rod, Egypt's standard unit of measurement, was carefully calibrated and used to ensure consistency across the entire construction project. Plumb bobs made from stone or metal allowed workers to establish perfectly vertical lines, while levels made from wood and water ensured that horizontal surfaces were true. These simple tools, when used by skilled craftsmen, could achieve a level of precision that rivals modern surveying equipment. The square, an L-shaped tool used to establish right angles, was essential for ensuring that the pyramid's corners were perfectly square. Egyptian squares were typically made from wood and carefully crafted to exact specifications. The accuracy of these tools was crucial to the geometric perfection of the finished pyramid, and master craftsmen would regularly check and adjust their squares to maintain precision throughout the construction process. Stone cutting techniques evolved throughout the pyramid building period, with craftsmen developing increasingly sophisticated methods for working with different types of stone. For limestone, workers would use copper chisels to cut along natural bedding planes in the rock, taking advantage of the stone's natural structure to achieve clean, flat surfaces. The process required patience and skill, as rushing could result in broken tools or damaged stone blocks. Working with granite presented different challenges, as this hard stone was much more resistant to copper tools. For granite cutting, workers relied more heavily on dolerite pounders and abrasive sand to gradually wear away the stone. This process was extremely time-consuming, which helps explain why granite was used sparingly in pyramid construction, reserved primarily for the most important internal chambers and facing stones. The technique of rubbing stones flat, mentioned in ancient texts, involved using sand as an abrasive medium between two stone surfaces. Workers would place sand between a rough stone block and a flat reference surface, then rub the stones together in a circular motion. This process would gradually wear away high spots on the rough stone, eventually creating a perfectly flat surface. This technique could achieve remarkable precision, producing surfaces that were flat to within fractions of an inch across large areas. Fire setting was another technique occasionally used by pyramid builders for working with particularly hard stone. Workers would build fires against rock faces to heat the stone, then suddenly cool it with water. The rapid temperature change would cause the stone to crack along natural fault lines, making it easier to break into manageable pieces. This technique required great skill and experience, as improper application could shatter valuable stone or create dangerous conditions for workers. The preservation and care of tools was a constant concern for pyramid construction crews. Copper tools were valuable and required careful maintenance to ensure their effectiveness. Workers would oil wooden tools to prevent cracking and splitting in the dry desert climate. Stone tools were regularly inspected for cracks and damage that might cause them to fail during use. The replacement and repair of tools represented a significant ongoing expense for the pyramid construction project. Tool making itself was a specialized craft that supported the pyramid construction effort. Skilled metalworkers not only manufactured new copper tools but also recycled worn implements, melting them down and recasting them into new chisels and other implements. Carpenters crafted the wooden handles for tools and created specialized implements for specific construction tasks. Stoneworkers shaped dolerite hammers and other stone tools, ensuring that construction crews had access to the implements they needed. The efficiency with which ancient Egyptian craftsmen used their simple tools is perhaps their greatest achievement. Through generations of experience and innovation, they developed techniques that maximized the effectiveness of copper, wood, stone, and rope. They understood the limitations of their materials and designed their methods accordingly, achieving results that seem impossible given the simplicity of their tools. The legacy of these ancient tools and techniques extends far beyond the pyramids themselves. The methods developed by Egyptian craftsmen influenced construction techniques throughout the ancient world and laid the foundation for many modern construction principles. The careful measurement, precise cutting, and methodical assembly techniques pioneered by pyramid builders remain relevant to construction work today. As we contemplate the simple tools used to build the pyramids, we are reminded that human ingenuity and skill can overcome seemingly insurmountable obstacles. The pyramid builders possessed no power tools, no steel implements, no advanced machinery, yet they created monuments that continue to amaze and inspire us nearly 5,000 years later. Their achievement stands as a testament to the power of human creativity and the remarkable results that can be achieved when simple tools are wielded by skilled and determined hands. The question that has puzzled engineers, archaeologists, and curious minds for centuries remains one of the most captivating mysteries of the ancient world. How did the pyramid builders lift millions of massive stone blocks, some weighing as much as modern trucks, to heights that would challenge even today's construction equipment? The Great Pyramid rises to a height equivalent to a 40-story building, yet it was constructed without cranes, without pulleys, and without any of the mechanical advantages we consider essential for modern construction. The theories that have emerged to explain this achievement range from the elegantly simple to the brilliantly complex, each offering insights into the ingenuity of ancient engineering. The most straightforward explanation for pyramid construction involves the use of ramps, massive earthen and stone causeways that would have allowed workers to drag heavy blocks up inclined planes to increasingly higher levels of the pyramid. This theory, first proposed by ancient historians and refined by modern researchers, suggests that the Egyptians built enormous ramps alongside or around the pyramid, creating pathways that teams of workers could use to transport stones from ground level to the upper reaches of the structure. The straight ramp theory envisions a single massive ramp extending from the base of the pyramid at a gentle incline that would allow workers to pull heavy sledges loaded with stone blocks. Such a ramp would need to maintain a grade of no more than 8 to 10 degrees to remain manageable for human haulers, which means that to reach the pyramid's apex, the ramp would need to extend over 1.5 kilometers from the pyramid's base. The volume of material required for such a ramp would be enormous, potentially requiring more stone and earth than the pyramid itself. Archaeological evidence for straight ramps remains limited, though some researchers point to remnants of what may have been construction ramps near other pyramids. The logistics of building and maintaining such massive ramps present their own challenges. The ramps would need to be constantly modified as the pyramid rose, requiring teams of workers dedicated solely to ramp construction and maintenance. As the pyramid neared completion, the ramps would become increasingly steep and difficult to navigate, potentially creating bottlenecks that would slow construction progress. The zigzag ramp theory offers a variation that addresses some of the limitations of straight ramps. This approach suggests that ramps were built in a series of switchbacks up the sides of the pyramid, allowing workers to reach higher levels without requiring the enormous lengths needed for straight ramps. The zigzag pattern would reduce the total volume of ramp material needed and could be modified more easily as construction progressed. However, this theory creates its own challenges, particularly in maneuvering heavy loads around the sharp turns required by the zigzag pattern. Recent archaeological work has revealed evidence that may support the zigzag ramp theory. Satellite imagery and ground-penetrating radar have identified what appear to be ramp remnants on some pyramid sites, showing patterns consistent with switchback construction. These discoveries have renewed interest in ramp-based theories and provided new directions for research into ancient construction methods. The internal spiral ramp theory, proposed by French architect Jean-Pierre Houdin, represents one of the most innovative recent explanations for pyramid construction. This theory suggests that the Egyptians built a ramp system inside the pyramid itself, creating a spiral pathway that wound through the interior of the structure as it rose. This internal ramp would have allowed workers to transport stones to upper levels without requiring the massive external ramps envisioned by earlier theories. Houdin's theory is based on detailed analysis of the pyramid's internal structure and anomalies in the stonework that may indicate the presence of internal passages. Computer modeling and architectural analysis suggest that an internal spiral ramp could provide an efficient means of reaching the pyramid's upper levels while minimizing the amount of ramp material needed. The theory also explains how the pyramid's precise outer casing stones could have been installed without interference from external ramps. The internal ramp theory addresses several puzzles that have long perplexed pyramid researchers. It explains how workers could have maintained access to the pyramid's upper levels throughout the construction process without building increasingly unwieldy external ramps. It also provides a mechanism for installing the pyramid's capstone and completing the uppermost courses of masonry without leaving evidence of massive ramp systems that would have been visible to later observers. Testing of the internal ramp theory has involved sophisticated imaging techniques, including cosmic ray detection and thermal analysis, designed to identify hidden chambers and passages within the pyramid. While these investigations have revealed some intriguing anomalies, definitive proof of internal ramps remains elusive. The theory continues to generate debate among researchers, with some embracing its elegance while others question whether such internal passages could have supported the heavy loads required for pyramid construction. Beyond ramp theories, researchers have explored the possibility that the pyramid builders used mechanical devices to lift heavy stones. The lever and counterweight system theory suggests that ancient engineers developed sophisticated lifting mechanisms using wooden beams, ropes, and stone counterweights to raise blocks vertically rather than dragging them up ramps. This approach would have required less ramp material but would have demanded greater mechanical sophistication. The use of levers for lifting heavy objects was well understood in the ancient world, and Egyptian workers certainly used simple levers for moving stones on level ground. Scaling this technology to lift multi-ton blocks to significant heights would have required engineering innovations that may not have left clear archaeological evidence. Some researchers have proposed that the Egyptians built temporary wooden lifting towers that could be dismantled and moved as construction progressed, leaving little trace for modern archaeologists to discover. Experimental archaeology has played a crucial role in testing various pyramid construction theories. Modern researchers have built scale models and conducted full-size experiments to evaluate the feasibility of different lifting methods. These experiments have demonstrated that teams of workers can indeed move very heavy stones using ropes, levers, and simple mechanical devices, though scaling these methods to the full size of pyramid construction remains challenging. One of the most ambitious experimental projects involved attempting to build a small pyramid using only tools and techniques available to ancient Egyptian workers. This project, carried out over several years, provided valuable insights into the challenges faced by ancient builders and demonstrated both the possibilities and limitations of various construction methods. The experiment showed that ancient techniques could indeed work, but required careful planning, skilled execution, and enormous human effort. The combination approach theory suggests that pyramid builders may have used multiple lifting methods depending on the specific challenges presented by different phases of construction. Early construction phases might have relied primarily on ramps for moving the massive core stones, while later phases could have used mechanical lifting devices for the more precise work of installing casing stones and completing upper levels. This flexible approach would have allowed builders to adapt their methods to changing conditions as the pyramid rose. The logistics of coordinating multiple lifting systems would have required sophisticated project management skills. Workers would need to be trained in different techniques, and the construction site would need to accommodate various types of equipment and materials. The ability to seamlessly transition between different construction methods would demonstrate the advanced organizational capabilities of ancient Egyptian engineers and administrators. Recent discoveries have provided new clues about pyramid construction methods. The discovery of papyrus documents from the reign of Khufu has revealed details about the transportation and organization of pyramid construction materials. These ancient administrative records describe the movement of limestone blocks and the coordination of work crews, providing unprecedented insights into the logistics of pyramid construction. The Wadi el-Jarf papyri, discovered at an ancient harbor site on the Red Sea coast, include logbooks kept by overseer Mera that describe the transportation of limestone from quarries to pyramid construction sites. These documents reveal the sophisticated administrative systems that supported pyramid construction and provide evidence for the scale and organization of the construction effort. The papyri also describe the use of boats for transporting heavy materials, suggesting that water transport played a larger role in pyramid construction than previously understood. The debate over pyramid construction methods continues to evolve as new evidence emerges and new analytical techniques become available. Advanced imaging technologies, computer modeling, and experimental archaeology are providing fresh perspectives on ancient construction methods. Each new discovery adds pieces to the puzzle, gradually building a more complete picture of how these ancient monuments were created. The persistence of the construction mystery speaks to the remarkable achievement of the pyramid builders. Despite decades of research and investigation, we continue to debate how these monuments were built, testament to the ingenuity and skill of their creators. The various theories proposed to explain pyramid construction reflect not just ancient capabilities, but also the creativity of modern researchers trying to understand and replicate ancient achievements. The study of pyramid construction methods has implications beyond archaeology and ancient history. Modern engineers and architects study ancient building techniques for insights that might inform contemporary construction challenges. The resourcefulness and efficiency demonstrated by pyramid builders offer lessons for modern construction projects, particularly in developing sustainable building methods that minimize environmental impact. As we contemplate the various theories about pyramid construction, we are reminded that great achievements often result from the creative combination of simple methods and techniques. The pyramid builders may not have possessed advanced machinery, but they had something equally valuable: the ability to envision solutions to unprecedented challenges and the determination to see those solutions through to completion. Their achievement stands as a testament to human ingenuity and the power of persistent effort in overcoming seemingly impossible obstacles. The story of the pyramids begins not on the Giza plateau, but in distant quarries where skilled workers carved the very foundations of eternity from living rock. These ancient quarries, scattered across Egypt from the limestone cliffs of Tura to the granite outcrops of Aswan, represent the starting point of one of history's most ambitious transportation networks. The journey of each stone block from quarry to pyramid involved challenges that would test the limits of ancient engineering. requiring the coordination of thousands of workers, hundreds of boats, and transportation systems that stretched across the length of Egypt. The scale of this undertaking reveals as much about ancient Egyptian civilization as the pyramids themselves. The primary source of stone for pyramid construction was the Giza plateau itself, where vast quantities of limestone lay beneath the desert surface. These local quarries, carved directly into the bedrock surrounding the pyramids, provided the bulk of the core stones that form the pyramid's internal structure. The quarrying process began with teams of workers identifying suitable stone layers, following geological formations that would yield blocks of consistent quality and size. The limestone at Giza, formed from ancient marine deposits, offered relatively soft stone that could be worked with copper tools, though even this manageable material required enormous effort to extract and shape. The techniques used to quarry limestone at Giza involved both skill and patience. Workers would begin by clearing away sand and debris to expose the bedrock beneath. They would then identify natural bedding planes in the limestone, following geological layers that would allow them to extract blocks with minimal waste. Using copper chisels and wooden wedges, quarrymen would carefully separate blocks from the surrounding rock, taking advantage of natural fractures and fault lines to achieve clean breaks. The process of extracting individual blocks required teams of specialized workers with different skills and responsibilities. Stone cutters would mark out the boundaries of each block, ensuring that the dimensions met the specifications required for pyramid construction. Wedge workers would drive wooden wedges into carefully placed holes using water to swell the wood and gradually split the stone along predetermined lines. Heavy laborers would use levers and ropes to extract the separated blocks and prepare them for transport to the construction site. The local Giza quarries gradually expanded into vast excavations that can still be seen today. These quarries, now partially filled with sand and debris, once reached depths of 30 meters or more, creating artificial canyons in the desert landscape. The scale of these excavations gives some indication of the enormous quantity of stone required for pyramid construction and the extent of the quarrying operations that supported the building effort. The finest limestone for pyramid construction came from quarries across the Nile River at Tura, about 15 kilometers south of Giza. The Tura limestone was prized for its fine grain and brilliant white color, making it ideal for the smooth outer casing that originally covered the entire pyramid. This high-quality stone was used for the pyramid's exterior surfaces and for internal chambers where appearance and precision were particularly important. The transportation of Tura limestone across the Nile and overland to Giza required sophisticated logistics and represented one of the major transportation challenges of pyramid construction. The Tura quarries were carved deep into the limestone cliffs on the eastern bank of the Nile, creating a network of underground galleries and chambers that honeycomb the cliff face. These subterranean quarries allowed workers to extract high-quality stone while protecting them from the harsh desert sun. The underground environment also provided more stable working conditions, with consistent temperatures and protection from sandstorms that could disrupt surface operations. Working in the Tura quarries required specialized skills and techniques adapted to the underground environment. Quarrymen worked by lamplight, using oil lamps and torches to illuminate their work areas. Ventilation was provided through carefully planned air shafts that brought fresh air to the working faces. The extraction process involved cutting blocks from the ceiling and walls of the galleries, requiring careful planning to prevent cave-ins and maintain safe working conditions. The granite blocks used in the pyramid's most important chambers came from quarries at Aswan, over 800 kilometers south of Giza. This journey, one of the longest regular transportation routes in the ancient world, required the coordination of quarrying operations, river transport, and overland movement across vast distances. The granite quarries at Aswan provided some of the hardest and most beautiful stone available to Egyptian builders, prized for its strength, durability, and distinctive appearance. The extraction of granite blocks at Aswan presented unique challenges that required different techniques from those used for limestone quarrying. Granite's hardness made it resistant to copper tools, forcing quarrymen to rely more heavily on stone hammers and abrasive techniques. The process of extracting large granite blocks could take weeks or even months, requiring patient and skilled work to achieve the precision needed for pyramid construction. The granite quarries at Aswan reveal the most sophisticated quarrying techniques developed by ancient Egyptian workers. Evidence at the site shows that quarrymen used a combination of fire setting, wedging, and pounding to extract granite blocks. Fire setting involved building fires against the rock face to heat the granite, then cooling it rapidly with water to create thermal stress that would crack the stone along natural fault lines. This technique, combined with careful wedging and pounding, allowed workers to extract granite blocks of enormous size and weight. The famous unfinished obelisk at Aswan, still attached to the bedrock, provides dramatic evidence of ancient quarrying techniques. This monument, which would have weighed over 1,000 tons when completed, shows the marks of the tools and methods used by ancient quarrymen. The precision of the cutting and the scale of the undertaking demonstrate the advanced skills possessed by Egyptian stoneworkers and their ability to plan and execute projects of unprecedented ambition. Transportation of quarried stone from Aswan to Giza relied primarily on the Nile River, Egypt's natural highway that connected the quarries with the construction sites. The annual flood of the Nile provided ideal conditions for transporting heavy loads, as the high water levels allowed large barges to navigate shallow areas and reduced the distance that stones had to be transported overland. The timing of quarrying and transportation operations was carefully coordinated with the flood cycle to take advantage of optimal river conditions. The boats used for transporting pyramid stones were marvels of ancient shipbuilding, designed specifically for carrying enormous loads on the Nile. These vessels, constructed from cedar wood imported from Lebanon, could carry loads of several hundred tons while maintaining the structural integrity needed for river navigation. The largest transport barges were among the biggest wooden vessels ever built in the ancient world, requiring skilled shipwrights and enormous quantities of high-quality timber. The design of stone transport barges reflected sophisticated understanding of naval architecture and load distribution. The boats featured reinforced hulls with multiple keels to spread the weight of heavy cargo and prevent the vessel from breaking apart under load. Special loading and unloading facilities were constructed at quarry sites and destination ports to handle the massive stone blocks safely and efficiently. The Wadi El Jaf papyri, discovered at an ancient harbor on the Red Sea coast, provide unprecedented insights into the logistics of stone transportation during pyramid construction. These documents, written by Overseer Mera and his crew, describe the transportation of limestone blocks from Tura quarries to Giza, revealing details about crew organization, transportation schedules, and the coordination required for major stone-moving operations. Mera's logbooks describe a transportation system of remarkable sophistication and scale. His crew operated a fleet of boats that regularly transported limestone blocks from Tura to Giza, following carefully planned schedules that coordinated with other transportation crews and construction activities. The documents reveal that transportation operations were organized with military precision, with detailed records kept of every shipment and careful attention paid to timing and coordination. The overland transportation of stone blocks from river ports to construction sites required different techniques and equipment from river transport. Heavy sledges, pulled by teams of workers or oxen, were used to move blocks across the desert terrain. The discovery that wetting the sand in front of sledges dramatically reduced the force required for pulling heavy loads represents one of the most important innovations in ancient transportation technology. Experimental archaeology has demonstrated the effectiveness of sand wetting techniques for reducing friction in sledge transport. When dry sand is wetted to the proper consistency, it forms a firmer surface that allows sledges to glide more easily. This technique, depicted in ancient Egyptian tomb paintings, could reduce the force required to pull heavy loads by as much as 50%, making it possible for smaller teams of workers to transport enormous stones. The logistics of coordinating stone transportation involved challenges that would test any ancient civilization. Transportation schedules had to be coordinated with quarrying operations, river conditions, and construction activities at pyramid sites. Weather, flood levels, and seasonal variations all affected transportation planning. The successful coordination of these complex operations required administrative skills and organizational capabilities that demonstrate the sophistication of ancient Egyptian management systems. The infrastructure required to support stone transportation was itself a major construction undertaking. Special harbors and loading facilities were built at quarry sites and destination ports. Roads and causeways were constructed to connect river ports with construction sites. Maintenance facilities were established to repair boats and equipment. This supporting infrastructure represented a significant investment that was essential to the success of pyramid construction projects. The human cost of stone transportation was enormous, requiring the coordination of thousands of workers across vast distances. Boat crews, dock workers, sledge teams, and support personnel all played essential roles in moving stones from quarries to construction sites. The physical demands of transportation work were severe, requiring strength, endurance, and skill that took years to develop. The seasonal nature of stone transportation created unique challenges for project planning and workforce management. Transportation operations were most efficient during the flood season when river levels were highest, but this was also the time when agricultural work was impossible and the largest workforce was available for construction activities. Coordinating transportation and construction schedules required careful planning and flexible management of human resources. The legacy of ancient Egyptian transportation systems extends far beyond pyramid construction. The techniques and organizational methods developed for moving pyramid stones influenced transportation throughout Egyptian history and provided models that were adopted by other ancient civilizations. The ability to move enormous loads across vast distances using simple technology demonstrates principles that remain relevant to modern transportation challenges. The study of ancient quarrying and transportation methods provides insights into the relationship between technology and organization in large-scale construction projects. The pyramid builders succeeded not because they possessed advanced technology, but because they developed sophisticated systems for coordinating human effort and simple technology to achieve unprecedented results. Their achievement demonstrates that complex projects can be accomplished through careful planning, skilled execution, and effective organization, even with limited technological resources. As we contemplate the vast network of quarries, transportation routes, and coordination systems that supported pyramid construction, we gain appreciation for the scope and complexity of ancient Egyptian achievements. The pyramids represent not just architectural marvels, but the successful coordination of one of history's most ambitious transportation and construction projects, demonstrating the power of human organization and determination to overcome seemingly impossible challenges. In the quiet hours before dawn, when the last stars fade into the growing light, we can imagine ancient Egyptian astronomers standing on the Giza plateau, their eyes turned skyward as they performed calculations that would determine the eternal resting place of their god-king. The precision achieved in pyramid construction goes far beyond mere building accuracy, reaching into the realm of astronomical perfection that connects these earthbound monuments to the cosmic order itself. The Great Pyramid's alignment with the cardinal directions, its mathematical relationships, and its geometric perfection represent achievements that challenge our understanding of ancient capabilities and reveal a civilization possessed of knowledge and skills that seem almost magical in their precision. The cardinal alignment of the Great Pyramid stands as perhaps the most remarkable demonstration of ancient Egyptian surveying capabilities. The monument faces true north with an accuracy that astounds modern engineers, deviating by less than 3 arc-minutes from perfect alignment. To appreciate this achievement, consider that 3 arc-minutes represents less than 1/20th of a degree, an error so small that it would be barely detectable without precise modern instruments. This level of accuracy suggests that the pyramid builders possessed surveying techniques of extraordinary sophistication, methods that allowed them to determine true north with a precision that rivals modern satellite-guided systems. The challenge of determining true north in the ancient world was far more complex than it might first appear. Unlike today, when we can simply use a magnetic compass, the ancient Egyptians had to rely on astronomical observations to establish direction. The magnetic compass would not be invented for another 3,000 years, and even if it had been available, magnetic north differs significantly from true north. The pyramid builders needed to find true north, the direction toward the Earth's rotational axis, and they achieved this using only naked-eye observations of the stars. The most likely method for determining true north involved observations of circumpolar stars, those stars that appear to circle around the north celestial pole without ever setting below the horizon. In the Pyramid Age, there was no bright star located exactly at the north celestial pole, unlike our modern Polaris. Instead, the ancient astronomers would have observed the circular paths of stars like Kochab and Mizar, noting the points where these stars reached their highest and lowest positions in their nightly journeys around the invisible pole. The technique of using circumpolar stars to find true north required patience, skill, and sophisticated understanding of celestial mechanics. Astronomers would construct observation platforms with carefully leveled surfaces and vertical markers, creating primitive but effective astronomical instruments. Over the course of many nights, they would track the movements of selected stars, noting the precise moments when the stars reached their extreme positions. By bisecting the angle between these extreme positions, they could determine the direction to the true celestial pole with remarkable accuracy. The process of transferring astronomical observations to the construction site required additional surveying techniques that demonstrate the mathematical sophistication of ancient Egyptian engineers. The direction established through star observations had to be marked on the ground and then used to orient the massive pyramid foundation. This transfer process involved the use of surveying rods, plumb lines, and geometric principles that allowed the astronomers precise measurements to guide the placement of millions of stone blocks. The leveling of the pyramid's foundation represents another triumph of ancient surveying precision. The base of the Great Pyramid varies in height by less than 2.1 centimeters across its entire 13-acre foundation, an achievement that would be impressive even by modern construction standards. This level of accuracy required surveying techniques that could detect and correct variations of less than an inch across distances of hundreds of meters, a challenge that pushed ancient surveying methods to their absolute limits. The ancient Egyptians achieved this remarkable leveling accuracy using water-based leveling techniques that took advantage of water's natural tendency to seek a uniform level. Surveyors would construct networks of channels and basins across the construction site, filling them with water to create reference levels that could be used to establish a perfectly horizontal foundation. This technique, while simple in principle, required careful engineering to account for factors like water temperature, surface tension, and the gradual settling of the foundation under the pyramid's enormous weight. The geometric perfection of the pyramid's shape reveals another dimension of ancient Egyptian mathematical knowledge. The Great Pyramid's slope angle of 51 degrees and 52 minutes creates a structure with remarkable mathematical properties. The ratio of the pyramid's height to the perimeter of its base approximates the mathematical constant pi, though scholars continue to debate whether this relationship was intentional or coincidental. Regardless of intent, the mathematical harmony embedded in the pyramid's proportions demonstrates sophisticated understanding of geometric principles. The construction techniques required to maintain geometric precision throughout the building process represent one of the most impressive aspects of pyramid engineering. As the pyramid rose level by level, builders had to ensure that each course of stones maintained the proper slope angle and that the structure remained square and symmetrical. Small errors in the placement of individual blocks could accumulate over the height of the pyramid, potentially causing significant deviations from the intended shape. The fact that the Great Pyramid maintains its geometric perfection to the very top demonstrates extraordinary quality control and construction management. The smoothing techniques used for the pyramid's surfaces reveal the advanced stoneworking capabilities of ancient Egyptian craftsmen. The exterior faces of the pyramid were originally covered with highly polished limestone casing stones that created a smooth, reflective surface visible from great distances. These casing stones were cut and fitted with joints so precise that the seams between blocks were nearly invisible. The techniques used to achieve this level of surface perfection involved careful selection of stone, precise cutting methods, and finishing processes that required both skill and patience. The internal chambers and passages of the Great Pyramid demonstrate precision that extends beyond the monument's external appearance. The floors of the chambers are level to within millimeters, the walls are perfectly plumb, and the corners meet at exact right angles. The passages maintain consistent dimensions throughout their length, with variations so small that they can only be detected with modern measuring instruments. This internal precision was achieved despite the enormous challenges of working in confined spaces deep within the pyramid structure. The alignment of the pyramid's internal passages with astronomical phenomena adds another layer to the precision story. The descending passage from the pyramid's entrance points toward the position where the star Thuban would have been visible in the Pyramid Age. The so-called star shafts from the king's and queen's chambers are oriented toward specific stars and constellations that held religious significance for the ancient Egyptians. These alignments required not only precise construction but also sophisticated astronomical knowledge and careful coordination between architects and astronomers. The methods used to achieve such precise internal alignments remain something of a mystery. Working inside the partially completed pyramid, with limited light and restricted access, builders somehow managed to orient passages and chambers to celestial targets with remarkable accuracy. This achievement suggests that the ancient Egyptians possessed surveying techniques that allowed them to transfer astronomical alignments from external observations to internal construction with minimal loss of accuracy. The precision of pyramid construction extends to details that are nearly invisible to casual observation but reveal themselves under careful measurement. The individual blocks used in construction were cut and fitted with tolerances measured in millimeters. The joints between blocks are so tight that it is often impossible to insert a knife blade between adjacent stones. This level of precision required not only skilled craftsmanship, but also quality control systems that ensured consistent standards throughout the construction process. The tools and techniques used to achieve such precision with ancient technology continue to puzzle researchers. The ancient Egyptians accomplished work that would challenge modern stone masons using only copper chisels, stone hammers, and measuring devices made from wood and rope. The methods they developed for cutting, moving, and positioning massive stone blocks with millimeter accuracy represent innovations that were far ahead of their time and demonstrate capabilities that seem almost impossible given their technological limitations. The cumulative effect of countless precise operations throughout pyramid construction creates an overall accuracy that staggers the imagination. Each measurement, each cut, each placement of stone had to be executed with care and precision to achieve the final result. The coordination required to maintain accuracy across thousands of workers and decades of construction demonstrates organizational capabilities that rival any modern project management system. The preservation of the pyramid's precision over nearly 5 millennia adds another dimension to the achievement. Despite earthquakes, thermal expansion and contraction, and the gradual settling of the foundation, the Great Pyramid has maintained its essential geometric properties with remarkably little distortion. This longevity demonstrates not only the precision of the original construction, but also the sophisticated understanding of materials science and structural engineering that guided the builder's work. The study of pyramid precision has benefited enormously from modern measuring technology, including laser surveying equipment, satellite positioning systems, and computer analysis. These tools have revealed details of pyramid construction that were invisible to earlier researchers and have provided new insights into ancient building techniques. However, each new measurement also raises new questions about how such precision was achieved with ancient methods and tools. The astronomical alignments of the pyramids reflect a worldview that saw deep connections between earthly and celestial realms. The precision of these alignments was not merely a demonstration of technical capability, but an expression of religious beliefs that linked the pharaoh's eternal journey with the movements of stars and planets. The accuracy achieved in these alignments suggests that astronomical precision was considered essential to the pyramid's spiritual function, not just its architectural success. The mathematical relationships embedded in pyramid design continue to inspire researchers and mathematicians who find new patterns and connections with each careful analysis. The pyramid's proportions relate to fundamental mathematical constants and geometric principles in ways that suggest sophisticated understanding of abstract mathematical concepts. Whether these relationships were consciously designed or emerged from practical construction considerations remains a subject of ongoing research and debate. The legacy of pyramid precision extends far beyond the monuments themselves, influencing construction techniques and quality standards throughout Egyptian history and beyond. The methods developed for achieving such accuracy became part of the technical knowledge that supported Egyptian civilization for thousands of years. The tradition of precision craftsmanship established during the Pyramid Age continued to characterize Egyptian architecture and engineering throughout the Pharaonic period. As we contemplate the extraordinary precision achieved in pyramid construction, we are reminded that human capabilities often exceed what we might consider possible given available technology. The pyramid builders possessed no power tools, no laser levels, no computer-controlled cutting equipment, yet they achieved results that would be impressive even by today's standards. Their achievement demonstrates that precision is not just a matter of technology, but of knowledge, skill, patience, and unwavering commitment to excellence. In the realm of human imagination, where mystery meets wonder, the pyramids have spawned theories that stretch far beyond the boundaries of conventional archaeology. These alternative explanations, ranging from the intriguingly possible to the fantastically improbable, reflect our deep fascination with these ancient monuments and our desire to find explanations that match the awe they inspire. While mainstream scholarship has built a compelling case for human achievement through skill and determination, the persistent allure of more exotic theories speaks to something profound in the human psyche: our need to believe that some accomplishments transcend ordinary capabilities and touch the realm of the extraordinary. The concept of lost ancient technology represents one of the most persistent alternative theories about pyramid construction. Proponents of this view suggest that the ancient Egyptians possessed knowledge and tools that have been lost to history, technologies that would explain the precision and scale of pyramid construction without requiring us to accept that such achievements were possible with copper tools and human labor alone. These theories often point to the apparent impossibility of moving massive stone blocks with ancient methods and the precision of construction that seems to exceed what should be possible with primitive tools. The lost technology hypothesis takes many forms, from relatively modest proposals about advanced metallurgy or sophisticated mechanical devices to more dramatic suggestions involving energy sources or construction methods unknown to modern science. Some researchers have suggested that the ancient Egyptians developed forms of concrete or artificial stone that would have made construction faster and more precise than traditional stone cutting methods. Others propose that they possessed advanced understanding of acoustics, magnetism, or other natural forces that could have been harnessed for construction purposes. The appeal of lost technology theories lies partly in their ability to bridge the gap between ancient achievements and modern understanding. If the pyramids seem too precise and too massive to have been built with copper chisels and ropes, then perhaps the ancient builders had access to more sophisticated tools that simply have not survived in the archaeological record. This explanation preserves our sense of wonder while providing a rational framework for understanding achievements that otherwise seem impossible. However, the lost technology hypothesis faces significant challenges when subjected to rigorous examination. Archaeological evidence consistently supports the use of simple tools and traditional construction methods throughout the pyramid building period. The tools found at pyramid sites, the quarry marks left by ancient workers, and the construction techniques visible in the monuments themselves all point to methods that, while sophisticated in their application, relied on technologies that were well within the capabilities of ancient civilizations. The water flotation theory represents a more specific variant of alternative construction explanations. This hypothesis suggests that the ancient Egyptians used water to float heavy stone blocks into position, either by flooding construction areas or by using water-filled chambers to provide buoyancy for massive stones. Proponents argue that this method would have eliminated the need for ramps or lifting devices while explaining how enormous blocks could be positioned with such precision. The water flotation concept draws inspiration from modern construction techniques that use water for moving heavy objects and from observations about the relationship between pyramid sites and ancient water levels. Some researchers have noted that the Giza plateau may have been closer to the Nile River in ancient times, and that seasonal flooding could have provided the water needed for flotation-based construction methods. The theory also points to the precision of stone placement as evidence that blocks were somehow suspended or floated into position rather than dragged and levered. Despite its initial appeal, the water flotation theory encounters practical difficulties when examined in detail. The amount of water required to float multi-ton stone blocks would be enormous, and the engineering challenges of containing and controlling such quantities of water would have been formidable even by modern standards. Additionally, archaeological evidence does not support the existence of the massive water management systems that would have been necessary for flotation-based construction. Sound and vibration theories represent some of the most intriguing alternative explanations for pyramid construction. These theories suggest that the ancient Egyptians understood principles of acoustic engineering that allowed them to use sound waves or vibrations to move heavy objects or to cut stone with greater precision than mechanical tools alone could achieve. Proponents point to the acoustic properties of pyramid chambers and to legends from various cultures that describe the use of sound for moving massive stones. The acoustic properties of pyramid chambers are indeed remarkable and may have been intentionally designed. The king's chamber in the Great Pyramid, when empty, resonates at a specific frequency that some researchers believe was deliberately created for ceremonial or spiritual purposes. The precision of the chamber's dimensions and the quality of its stonework certainly suggest that acoustic considerations played a role in its design. Whether these acoustic properties could have been used for construction purposes remains highly speculative. Resonance and vibration theories often invoke modern understanding of physics to suggest that ancient builders might have discovered natural phenomena that could assist in construction. The idea that specific frequencies could reduce the effective weight of objects or make stone easier to cut has captured the imagination of many researchers. However, the physical principles that would be required for such effects are not supported by current scientific understanding, and no credible mechanism has been proposed for how sound waves could provide the dramatic assistance to construction that these theories require. The ancient alien hypothesis represents perhaps the most famous and controversial alternative explanation for pyramid construction, popularized by authors like Erich von Däniken and perpetuated by numerous television programs and books. This theory suggests that the pyramids were built with the assistance of extraterrestrial visitors who possessed advanced technology far beyond ancient human capabilities. Proponents argue that the precision and scale of pyramid construction provide evidence of non-human intervention in ancient Egyptian civilization. The ancient alien theory often focuses on specific aspects of pyramid construction that seem difficult to explain through conventional means. The precision of stone cutting, the massive size of some blocks, and the mathematical relationships embedded in pyramid design are all cited as evidence that the monuments exceed what ancient humans could have accomplished independently. The theory also draws on similarities between pyramid designs and modern technological concepts, suggesting that the monuments reflect knowledge that could only have come from an advanced technological civilization. Despite its popular appeal, the ancient alien hypothesis faces overwhelming opposition from the scientific community. Archaeological evidence consistently supports human construction of the pyramids using methods and tools that were available to ancient Egyptian civilization. The gradual development of pyramid building techniques visible in the archaeological record shows a clear progression of human learning and innovation rather than the sudden appearance of advanced technology. The social and cultural context of pyramid construction, including the complex religious and political motivations that drove these projects, reflects thoroughly human concerns and capabilities. The rejection of ancient alien theories by mainstream scholarship is not based on bias or closed-mindedness, but on the fundamental principle that extraordinary claims require extraordinary evidence. While the pyramids are indeed remarkable achievements, they fall within the range of what human civilization has demonstrated itself capable of accomplishing through organization, skill, and determination. The assumption that ancient peoples could not have achieved such monuments without outside assistance reflects a profound underestimation of human capabilities and ingenuity. Critical thinking about alternative pyramid theories requires careful evaluation of evidence and claims. The most important distinction to make is between hypotheses that are based on physical evidence and those that rely primarily on speculation or gaps in our current knowledge. Legitimate scientific theories must be testable and must make predictions that can be verified through observation and experiment. Theories that cannot be tested or that require us to ignore substantial contradictory evidence fail to meet the standards of scientific inquiry. The persistence of alternative theories about pyramid construction reflects deeper aspects of human psychology and culture. The pyramids represent achievements that inspire awe and wonder, emotions that naturally lead us to seek explanations that match the magnitude of our response. When conventional explanations seem insufficient to account for our sense of amazement, we may be drawn to more exotic possibilities that better reflect our emotional reaction to these monuments. The role of mystery in human culture also contributes to the appeal of alternative theories. Mysteries engage our imagination and provide opportunities for speculation and wonder that purely factual explanations may not satisfy. The idea that we still do not fully understand how the pyramids were built preserves a sense of mystery that many people find more appealing than complete technical understanding. Alternative theories offer ways to maintain this sense of mystery while providing explanations that seem to match the monument's impressive scale. The educational value of examining alternative theories lies not in accepting them uncritically, but in understanding the process of critical evaluation and the importance of evidence-based reasoning. By examining why certain theories appeal to us and how they measure against available evidence, we can develop better skills for evaluating claims and understanding the difference between speculation and knowledge. The pyramids provide an excellent case study for exploring these important intellectual skills. The relationship between mainstream archaeology and alternative theories is often characterized by tension, but it need not be adversarial. Legitimate questions about pyramid construction continue to challenge researchers and drive new investigations. The precision of construction, the logistics of organization, and the technical innovations of ancient builders all deserve continued study and may yield new insights as research methods and technologies advance. The key is to maintain rigorous standards for evidence while remaining open to new discoveries and interpretations. The social and cultural impact of alternative pyramid theories extends beyond academic circles to influence popular understanding of ancient history and human capabilities. These theories shape how people think about the past and about the relationship between ancient and modern civilizations. The responsibility of educators and researchers is to provide accurate information while acknowledging the legitimate sense of wonder that the pyramids inspire and the natural human tendency to seek explanations for remarkable achievements. The future of pyramid research will likely continue to generate new theories and interpretations as technology advances and new evidence emerges. Advanced imaging techniques, computer modeling, and other analytical tools may reveal previously unknown aspects of pyramid construction that could modify our understanding of ancient building methods. The important principle is to remain committed to evidence-based reasoning while maintaining appreciation for the remarkable achievements that the pyramids represent. As we contemplate the various alternative theories about pyramid construction, we are reminded that the human desire to understand and explain remarkable achievements is itself a testament to the curiosity and imagination that drives scientific inquiry. While we must evaluate theories critically and base our understanding on solid evidence, we can also appreciate the sense of wonder that motivates alternative explanations and use that wonder as inspiration for continued learning and discovery. The pyramids remain monuments not just to ancient achievement, but to the human quest for understanding that continues to this day. In the gentle hours of twilight, when the setting sun casts long shadows across the Giza plateau and the pyramids stand silhouetted against the deepening sky, we might pause to consider not just how these monuments were built, but why they were conceived in such a specific and extraordinary form. The pyramid shape, with its square base and triangular faces rising to a perfect point, was not chosen by accident or convenience. This geometric form emerged from the deepest beliefs of ancient Egyptian civilization, embodying religious concepts, cosmic understanding, and spiritual aspirations that reached far beyond the practical needs of burial architecture. To understand why the pyramids were built as they were, we must journey into the sacred landscape of ancient Egyptian thought, where the boundaries between earth and heaven, between mortal life and eternal existence, were bridged by monuments designed to last forever. The pyramid shape itself held profound symbolic meaning in ancient Egyptian religious thought, representing the primordial mound that emerged from the waters of chaos at the creation of the world. According to Egyptian mythology, this first hill was the place where the sun god Ra first appeared, bringing light and order to the universe. By constructing their pharaoh's tomb in the form of a pyramid, the ancient Egyptians were recreating this moment of cosmic birth, ensuring that their god-king would participate in the eternal cycle of death and rebirth that governed both the sun's daily journey and the rhythm of the seasons. The pyramid's triangular faces were understood to represent the rays of the sun, frozen in stone and pointing eternally skyward. This connection to solar symbolism was central to Egyptian religious thought, which saw the pharaoh as the earthly embodiment of the sun god. The pyramid's shape allowed the deceased pharaoh to ascend to heaven along these stone rays, following the same path that the sun took in its daily journey across the sky. The brilliant white limestone casing that originally covered the pyramids would have reflected sunlight with dazzling intensity, making the monuments appear to glow like captured starlight in the desert landscape. The mathematical precision embedded in pyramid design reflects not just engineering skill, but also religious concepts about cosmic order and divine perfection. The ancient Egyptians believed that the universe was governed by Ma'at, a principle of truth, justice, and cosmic harmony that maintained the balance between order and chaos. The geometric perfection of the pyramids embodied this principle in stone, creating monuments that reflected the mathematical harmony that the Egyptians saw in the movements of stars and planets, the flooding of the Nile, and the cycles of agricultural life. The orientation of the pyramids to the cardinal directions connected these earthbound monuments to the cosmic order in ways that were both practical and symbolic. The precise alignment with true north linked the pyramid to the axis around which the heavens appeared to rotate, making the monument a kind of cosmic anchor that participated in the eternal stability of the universe. This alignment was not merely decorative but served the practical purpose of ensuring that the pharaoh's spirit could navigate the celestial landscape and find its proper place among the circumpolar stars that never set. The internal structure of the pyramids reflects sophisticated understanding of the pharaoh's journey to the afterlife and the practical requirements for ensuring his successful transformation into a divine being. The chambers and passages within the pyramid were not simply storage spaces for burial goods, but represented way stations on the pharaoh's spiritual journey. The ascending passages symbolized the soul's upward movement toward divine transformation, while the chambers themselves provided spaces for the complex rituals that would ensure the pharaoh's successful resurrection and eternal life. The relationship between pyramid design and stellar alignments reveals another dimension of the religious thinking that shaped these monuments. The ancient Egyptians saw deep connections between earthly events and celestial movements, believing that the pharaoh's destiny was written in the stars and that his tomb should reflect these cosmic relationships. The star shafts in the Great Pyramid, which point toward specific constellations and stars, were designed to ensure that the pharaoh's spirit could travel to its proper place in the celestial realm and participate in the eternal journey of the gods. The constellation of Orion held particular significance in pyramid symbolism, as it was associated with Osiris, the god of the dead and the underworld. The ancient Egyptians saw in Orion's annual cycle of disappearance and reappearance a reflection of the death and resurrection cycle that they hoped to achieve for their pharaoh. By aligning pyramid passages with Orion, the builders created a permanent connection between the earthbound tomb and the celestial realm where Osiris ruled, ensuring that the pharaoh would find his way to divine resurrection. The massive scale of pyramid construction served purposes that went far beyond the practical needs of burial architecture. These monuments were designed to demonstrate the pharaoh's divine power and his ability to mobilize the resources of an entire kingdom in service of eternal life. The pyramid's enormous size and perfect construction proclaimed to all observers, both contemporary and future, that the pharaoh possessed godlike powers that transcended ordinary human capabilities. This demonstration of power served important political purposes, reinforcing the pharaoh's authority and legitimizing his divine status in the eyes of his subjects. The pyramid complex as a whole functioned as a cosmic machine designed to ensure the pharaoh's successful transition to divine status and his continued effectiveness as a god-king in the afterlife. The various elements of the complex, including temples, causeways, smaller pyramids, and subsidiary structures, all played roles in the elaborate rituals that would maintain the pharaoh's divine power after death. These rituals were not one-time ceremonies, but ongoing activities that would continue for generations, requiring permanent institutions and endowments to ensure their perpetuation. The economic and social implications of pyramid construction were themselves expressions of religious belief about the pharaoh's divine nature and cosmic responsibilities. The enormous resources devoted to pyramid building represented not waste or extravagance, but necessary investment in the spiritual infrastructure that would ensure the continued prosperity and stability of the kingdom. The pharaoh's successful transformation into a god was believed to benefit all of Egypt, providing divine protection and ensuring the continuation of Ma'at throughout the land. The architectural innovations developed for pyramid construction reflected religious concepts about permanence and eternity that were central to ancient Egyptian thought. The pyramid was designed to last forever, embodying the Egyptian belief that some aspects of existence transcend the temporal world and participate in eternal reality. The precision of construction, the quality of materials, and the sophisticated engineering all served the religious purpose of creating a monument that would endure until the end of time, providing a permanent bridge between earthly and divine realms. The pyramid's internal chambers were designed according to religious texts and beliefs about the afterlife journey that provide detailed maps of the spiritual landscape the pharaoh would navigate after death. The pyramid texts, among the oldest religious writings in the world, describe the various challenges and transformations that the pharaoh would face in his journey to divine status. The physical design of pyramid chambers and passages reflects these textual descriptions, creating three-dimensional representations of spiritual concepts that would assist the pharaoh in his cosmic journey. The relationship between pyramid construction and the agricultural cycle reflects deep Egyptian beliefs about the connection between earthly fertility and cosmic order. The annual flooding of the Nile, which brought life to the desert and enabled Egyptian civilization, was seen as an earthly reflection of cosmic processes that governed death and rebirth throughout the universe. The timing of pyramid construction activities to coincide with agricultural seasons ensured that these monuments participated in the same cosmic rhythms that governed all life in Egypt. The social organization required for pyramid construction embodied religious concepts about cosmic order and divine hierarchy that were fundamental to Egyptian civilization. The coordinated efforts of thousands of workers, the precise planning required for such massive projects, and the administrative systems needed to support construction all reflected the Egyptian belief that earthly society should mirror the perfect order of the divine realm. The pyramid project became a way of creating heaven on earth, organizing human society according to divine principles. The technological innovations developed for pyramid construction were driven by religious imperatives that demanded perfection in service of the divine pharaoh. The precision of stone cutting, the accuracy of astronomical alignments, and the sophistication of construction techniques all reflected the Egyptian belief that offerings to the gods, including the pharaoh's tomb, should be as perfect as humanly possible. This religious motivation drove technological advancement and innovation in ways that purely practical considerations might not have achieved. The artistic and symbolic elements incorporated into pyramid design served as permanent prayers and magical formulae intended to assist the pharaoh in his afterlife journey. The hieroglyphic inscriptions, the geometric proportions, and even the choice of building materials all carried symbolic meanings that were believed to possess actual power to transform spiritual reality. The pyramid was not just a tomb, but a magical instrument designed to guarantee the pharaoh's successful transformation into a god. The legacy of pyramid symbolism extended far beyond the monuments themselves, influencing Egyptian art, architecture, and religious thought for thousands of years. The pyramid shape became a permanent part of Egyptian symbolic vocabulary, appearing in smaller monuments, decorative elements, and religious artifacts throughout Egyptian history. The concepts embodied in pyramid design, including the connection between geometric perfection and divine power, continued to influence Egyptian culture long after the Great Age of pyramid building had ended. The international influence of pyramid symbolism demonstrates the power of these monuments to communicate religious and political concepts across cultural boundaries. The pyramid shape was adopted by other civilizations, including the Nubians, Greeks, and Romans, who recognized in these monuments powerful symbols of divine authority and cosmic order. The enduring fascination with pyramids in modern culture reflects the continuing power of these ancient symbols to evoke concepts of mystery, permanence, and transcendence. The environmental integration of pyramid complexes with the natural landscape reflects Egyptian beliefs about the sacred geography that connected earthly locations with cosmic realities. The choice of the Giza Plateau as a pyramid site was not arbitrary, but reflected careful consideration of the location's relationship to the Nile, to prevailing winds, and to the movement of celestial bodies. The pyramid complex was designed to harmonize with natural features while transforming the landscape into a sacred space that would serve divine purposes for eternity. As we contemplate the religious and symbolic purposes that shaped pyramid construction, we gain insight into a civilization that saw no separation between practical achievement and spiritual aspiration. The pyramids were built not as mere tombs or monuments to ego, but as instruments of cosmic transformation, designed to ensure the continued divine protection of Egypt and the eternal prosperity of its people. Their enduring power to inspire awe and wonder reflects their success in embodying timeless human aspirations for permanence, meaning, and connection to something greater than our mortal existence. As we stand in our modern world of glass towers and steel bridges, of computer-designed structures and satellite-guided construction, the ancient pyramids continue to speak to us across the millennia with lessons that transcend their original purpose. These monuments, conceived in an age when the wheel was still a novel invention and copper represented the height of metallurgical achievement, offer insights that remain profoundly relevant to our contemporary challenges. The pyramids teach us not just about ancient capabilities, but about timeless principles of human organization, environmental harmony, and the power of shared vision that can guide us as we face the complex problems of our own era. The organizational lessons embedded in pyramid construction speak directly to modern challenges in project management and large-scale coordination. The ancient Egyptians accomplished what may have been history's most complex construction project by developing systems of planning, communication, and resource management that enabled them to coordinate the efforts of tens of thousands of workers across multiple decades. Their achievement demonstrates principles of organization that remain relevant to any large-scale human endeavor, from modern construction projects to space exploration and global efforts to address climate change. The pyramid builders understood that successful completion of massive projects requires not just technical knowledge, but also sophisticated systems for managing human resources and maintaining motivation over extended periods. They developed rotation systems that allowed workers to contribute to the project while maintaining their other responsibilities, created support infrastructure that ensured worker health and welfare, and established quality control systems that maintained standards across the entire construction effort. These organizational innovations provide models for modern project managers who must coordinate complex efforts involving multiple stakeholders and extended timelines. The sustainability lessons offered by pyramid construction are particularly relevant as we face contemporary environmental challenges. The ancient Egyptians built monuments designed to last for millennia, using local materials and construction techniques that worked in harmony with natural systems rather than against them. Their approach to construction prioritized durability and long-term thinking over short-term convenience, creating structures that have endured for nearly 5,000 years with minimal maintenance or repair. The pyramid builders' use of local materials demonstrates principles of sustainable construction that modern architects and engineers are rediscovering. Rather than transporting materials across vast distances, they utilize the resources available in their immediate environment, adapting their construction techniques to work with the properties of local stone and taking advantage of natural features like the Nile flood cycle to facilitate transportation. This approach minimized environmental impact while creating structures that were perfectly adapted to their local conditions. The precision and quality standards maintained throughout pyramid construction offer lessons about the relationship between craftsmanship and durability that are increasingly relevant in our age of planned obsolescence. The ancient builders understood that investing time and effort in precise construction and high-quality materials would pay dividends over centuries and millennia. Their commitment to excellence in every aspect of construction, from the cutting of individual stones to the alignment of the entire structure, created monuments that have outlasted most subsequent civilizations. The educational value of pyramid construction extends beyond technical lessons to encompass broader insights about human potential and the power of organized effort. The pyramids demonstrate that seemingly impossible goals can be achieved through careful planning, persistent effort, and the coordination of individual skills and talents. This lesson is particularly relevant in our modern world, where complex global challenges require unprecedented levels of international cooperation and coordination. The pyramids also teach us about the importance of vision and shared purpose in motivating collective action. The ancient Egyptians were willing to devote enormous resources and decades of effort to pyramid construction because these projects embodied values and aspirations that resonated throughout their society. The monuments represented not just tombs for pharaohs, but expressions of cosmic order, religious devotion, and national identity that gave meaning to individual sacrifice and effort. The technological innovations developed for pyramid construction demonstrate how practical challenges can drive advances in human knowledge and capability. The need to move massive stones, achieve precise measurements, and coordinate complex logistics forced the ancient Egyptians to develop new tools, techniques, and organizational methods that found applications far beyond pyramid construction. This pattern of innovation driven by ambitious goals provides a model for how contemporary challenges might spur advances in technology and human capability. The interdisciplinary nature of pyramid construction offers lessons about the value of integrating different fields of knowledge and expertise. The successful completion of these monuments required coordination between astronomers and architects, engineers and artists, administrators and craftsmen. This integration of diverse skills and perspectives enabled the ancient Egyptians to achieve results that no single discipline could have accomplished independently. Modern challenges similarly require interdisciplinary approaches that break down barriers between different fields of knowledge. The pyramids demonstrate the importance of maintaining institutional knowledge and continuity across generations. The construction of these monuments required not just the skills and knowledge of individual craftsmen, but also systems for training successors and preserving technical knowledge across decades of construction time. The ancient Egyptians developed educational institutions and apprenticeship systems that ensured the continuity of specialized knowledge, providing models for how modern societies can maintain and develop technical expertise. The precision achieved in pyramid construction without modern measuring instruments offers insights into the relationship between technology and human capability. The ancient builders achieved remarkable accuracy using simple tools combined with sophisticated techniques and careful attention to detail. Their achievement suggests that technological advancement is not just about developing new tools, but also about refining our understanding of how to use available resources most effectively. The social organization required for pyramid construction provides lessons about leadership and motivation that remain relevant to contemporary management challenges. The pyramid builders had to maintain worker morale and productivity across decades of difficult labor, coordinate the efforts of diverse groups with different skills and backgrounds, and ensure quality control across enormous and complex projects. Their success in these areas demonstrates leadership principles that transcend the specific context of ancient construction. The economic principles underlying pyramid construction offer insights into the relationship between investment and long-term value creation. The enormous resources devoted to pyramid building represented not consumption or waste, but investment in projects that would provide benefits for millennia. This long-term perspective on value creation provides a model for contemporary decisions about infrastructure investment and resource allocation, particularly in areas like education, research, and environmental protection. The pyramid builders' approach to problem-solving demonstrates the value of iterative improvement and learning from experience. The evolution of pyramid construction techniques across the centuries shows a pattern of continuous refinement and innovation, with each generation of builders improving upon the methods of their predecessors. This approach to continuous improvement provides a model for how modern organizations and societies can adapt and evolve to meet changing challenges. The international influence of pyramid construction demonstrates how achievements in one culture can inspire and influence developments across the world. The monuments at Giza became models for similar projects in other civilizations, and continue to inspire architectural and engineering projects today. This pattern of cross-cultural influence and inspiration provides insights into how innovations and achievements can have impact far beyond their original context. The preservation of pyramid knowledge through written records and archaeological evidence demonstrates the importance of documentation and knowledge preservation for future generations. The ancient Egyptians left detailed records of construction techniques, organizational methods, and design principles that continue to inform our understanding thousands of years later. Their commitment to preserving knowledge provides a model for how contemporary societies can ensure that important innovations and insights are passed on to future generations. The spiritual and philosophical dimensions of pyramid construction offer lessons about the relationship between material achievement and deeper human aspirations. The pyramids were not built merely as practical structures, but as expressions of beliefs about meaning, purpose, and humanity's place in the cosmic order. This integration of practical achievement with spiritual aspiration provides a model for how contemporary projects might address not just immediate needs, but also deeper human values and aspirations. The resilience demonstrated by pyramid construction in the face of enormous challenges offers inspiration for contemporary efforts to address complex global problems. The ancient builders faced obstacles that seemed insurmountable, yet persevered through decades of difficult work to achieve their goals. Their example demonstrates that persistent effort and creative problem-solving can overcome seemingly impossible obstacles, providing encouragement for contemporary efforts to address challenges like climate change, poverty, and disease. The collaborative nature of pyramid construction demonstrates the power of collective effort and shared commitment to achieve goals that exceed individual capabilities. The monuments at Giza represent the coordinated efforts of thousands of individuals working together toward a common purpose, each contributing their skills and labor to create something greater than any could have achieved alone. This lesson about the power of collaboration remains profoundly relevant to contemporary challenges that require coordinated global responses. As we reflect on the lessons offered by these ancient monuments, we are reminded that human achievement transcends the particular technologies and circumstances of any given era. The pyramids teach us that with vision, organization, persistence, and collaborative effort, human societies can accomplish goals that seem impossible and create works that endure far beyond their creators. These timeless lessons continue to inspire and guide us as we face the challenges and opportunities of our own time, reminding us that the human capacity for achievement knows no bounds when guided by wisdom, sustained by determination, and unified by shared purpose. In the quiet darkness of a desert night, beneath a canopy of stars that have watched over these ancient monuments for nearly 5 millennia, the pyramids of Giza stand as they have since the dawn of recorded history, their massive forms silhouetted against the eternal sky. The gentle night breeze carries whispers of sand across their weathered surfaces, the same wind that cooled the brows of their builders and witnessed the completion of humanity's most enduring architectural achievement. As our journey through the mysteries of pyramid construction draws to a close, we find ourselves not with all the answers we might have hoped for, but with something perhaps more valuable, a deeper appreciation for the remarkable capabilities of human ingenuity and the timeless power of shared vision. The pyramids were built to last forever, and they very nearly have. Through 47 centuries of earthquakes and sandstorms, of rising and falling civilizations, of conquest and cultural transformation, these monuments have endured while empires have crumbled into dust around them. The pharaohs who commissioned them have long since completed their journey to whatever afterlife awaited them, yet their stone legacy continues to speak across the ages, whispering secrets about human potential that each generation must rediscover for itself. Though we have come closer than ever before to understanding the practical methods of pyramid construction, these monuments still speak in riddles that challenge our assumptions about ancient capabilities and human achievement. Each new archaeological discovery, each advanced measurement technique, each computer simulation designed to test construction theories adds new pieces to an ancient puzzle that seems to grow more complex, even as our knowledge expands. The precision of construction that rivals modern standards, the organizational sophistication that coordinated tens of thousands of workers, the astronomical knowledge that achieved perfect celestial alignments all point to a civilization whose capabilities we are only beginning to appreciate. Perhaps this persistence of mystery is itself part of the pyramid's greatest power. In our age of instant information and complete explanations, these ancient monuments remind us that some achievements transcend simple understanding and continue to inspire wonder, no matter how much we learn about them. The pyramids force us to confront the limitations of our knowledge while simultaneously expanding our conception of what human beings can accomplish when they unite around a common purpose and persist through seemingly impossible challenges. The builders of the pyramids worked without the benefit of steel tools or modern machinery, without computers to calculate loads and stresses, without cranes to lift massive stones or trucks to transport them across vast distances. Yet they created monuments that embody mathematical precision, astronomical knowledge, and engineering sophistication that continues to amaze contemporary experts. Their achievement reminds us that human capability is not limited by available technology, but by imagination, determination, and the willingness to push beyond perceived limitations. The social organization required to complete these monuments reveals insights about human cooperation that remain relevant to our contemporary world. The pyramid builders developed systems of coordination and motivation that enabled them to sustain massive collective efforts across multiple generations. They created institutions that preserved knowledge, maintained quality standards, and ensured the continuity of purpose necessary for projects that outlasted individual lifetimes. Their success demonstrates principles of leadership, organization, and shared commitment that transcend the specific context of ancient construction. The spiritual dimensions of pyramid construction add layers of meaning that extend far beyond their function as tombs or monuments to royal power. These structures embody humanity's eternal quest to create something lasting, something that transcends the boundaries of mortal existence and connects earthly achievement with cosmic purpose. The pyramid builders understood that their work was not merely practical construction, but participation in a sacred enterprise that would bridge the gap between temporal and eternal reality. The environmental lessons embedded in pyramid construction speak to contemporary concerns about sustainability and harmony with natural systems. The ancient builders created monuments designed to last for millennia using local materials and construction methods that worked with rather than against environmental conditions. Their approach demonstrates principles of sustainable development that prioritize long-term thinking over short-term convenience, creating works that enhance rather than degrade their natural setting. The technological innovations developed for pyramid construction illustrate how ambitious goals can drive advances in human knowledge and capability. The need to achieve unprecedented precision and scale forced the ancient Egyptians to develop new tools, techniques, and organizational methods that found applications far beyond their original purpose. This pattern of innovation driven by visionary goals provides a model for how contemporary challenges might inspire breakthrough advances in science and technology. The international influence of pyramid construction demonstrates how great achievements can inspire and influence cultures across vast distances and time periods. The monuments at Giza became models for similar projects throughout the ancient world and continue to influence architecture and engineering today. Their enduring power to capture human imagination speaks to universal aspirations for permanence, beauty, and transcendence that connect us across cultural and temporal boundaries. The study of pyramid construction continues to evolve as new technologies and research methods provide fresh perspectives on ancient achievements. Advanced imaging techniques reveal previously hidden details of construction methods. Computer modeling allows researchers to test theories about lifting and transportation with unprecedented precision. Archaeological discoveries provide new insights into the social and economic systems that supported these massive projects. Each new development adds to our understanding while often raising new questions about ancient capabilities. The preservation of pyramid knowledge through written records and archaeological evidence demonstrates the importance of maintaining cultural memory and passing wisdom to future generations. The ancient Egyptians understood that their achievements would be meaningless if the knowledge and principles that made them possible were lost. They created systems for preserving technical knowledge, training skilled craftsmen and maintaining institutional continuity that ensured their innovations would survive and inspire future generations. The collaborative nature of pyramid construction offers inspiration for contemporary efforts to address global challenges that require unprecedented cooperation and coordination. The monuments at Giza represent the successful integration of diverse skills, backgrounds, and perspectives in service of goals that exceeded any individual capability. This model of collective achievement provides guidance for how modern societies might organize themselves to address complex problems that require sustained cooperation across multiple generations. As we stand in imagination at the base of these ancient monuments, feeling the weight of their massive stones and the precision of their construction, we are reminded that human achievement knows no bounds when guided by vision, sustained by determination, and unified by shared purpose. The pyramid builders possessed no advanced technology in the modern sense, yet they accomplished something that continues to challenge our understanding and inspire our admiration nearly 5,000 years later. The mystery of the pyramids lies not in any single aspect of their construction, but in the totality of human achievement they represent. They embody the convergence of technical skill and spiritual vision, of individual excellence and collective effort, of practical innovation and cosmic aspiration. They demonstrate that human beings, working together with patience and determination, can create works that transcend the limitations of their time and speak to fundamental truths about human potential. The pyramids remain monuments not just to ancient achievement but to the enduring human capacity for wonder, for reaching beyond immediate needs towards something greater and more lasting. They remind us that our species is capable of remarkable things when we dare to envision goals that exceed our current capabilities and commit ourselves to the long journey of making those visions reality. In the end, perhaps the true legacy of the pyramids lies not in how they were built, but in their power to inspire us to reach for our own impossibilities, to imagine our own monuments to human potential, and to remember that the greatest achievements in human history have always been the result of people who refused to accept that something could not be done. The pyramids stand as eternal testimony to the power of human dreams made manifest in stone, reminders that we too can build works that will outlast our time and speak to future generations about the heights that human determination can reach.